Hey guys, in this video, we're going to talk about phase changes and heating and cooling curves. So our learning objective is to describe the changes of state between solids, liquids, and gases in terms of energy and how that can be represented by a heating or cooling curve. And so obviously we've talked a little bit about different phases of matter here. You have solids where the particles are very close together. They have definite shape and definite volume. Liquids, the particles are still very close together. They have definite volume, indefinite shape. They're going to take the shape of whatever container you put them in. And then gases have that indefinite shape, indefinite volume, and the particles move very quickly and have very little attraction to one another, and there's a lot of space in between the particles. So, melting, freezing, sublimation, deposition. So these are phase changes. So a change of state occurs when a substance is converted from one state to another. And really, let's just put this simply. All phase changes are a result of changes in temperature resulting from the gain or loss of heat energy. And it's all about what the particles are doing. Are the particles moving really slowly and locked in place right next to each other? Are the particles moving a little bit faster and able to flow over one another, but they still have a very strong attraction to one another like they do in a liquid? Or are the particles moving extremely fast and have no attraction to one another as they do in a gas? And so as we add energy here, you can see going from left to right, as we add energy to a solid, think of a chunk of ice. You put a chunk of ice onto let's say you put it in a pan and put it on the stove, and you don't even turn the burner on. Well, eventually that ice cube is going to start to melt because the energy that you're adding is the difference in temperature from being in the kitchen versus being in the freezer. So then we turn the heat up on that ice cube. That ice cube has begun to melt, and now it's all liquid. So then we turn our burner on, and now the heat begins to go much higher than the 72 degrees Fahrenheit that the room temperature is, And so then we get that up to 100 degrees Celsius or 212 degrees Fahrenheit to where it's boiling. Well, that boiling point is where the liquid water begins to turn into a gas. Again, we're adding energy there, and those particles are moving faster, and that faster motion means that they have less of an attraction for each other. And then vice versa, if we go the other way, if we start to cool down a gas, we can convert it into a liquid, cool down that liquid even more, take more energy away, it turns into a solid. So phase changes, there are endothermic and exothermic phase changes. And it might almost seem the opposite of what you might just logically think. So endothermic processes, or those that involve the gain of heat energy, are as follows. Melting. Melting is an endothermic process. A solid changes into a liquid. So as that ice cube is sitting there, it's absorbing energy from its surroundings, making the molecules move a little quicker until it turns into a liquid. The melting point is the temperature at which a solid turns into a liquid. Evaporation. So evaporation is where you have a liquid changing into a gas. Boiling point is the temperature at which a liquid turns into a gas. And so there's a couple different variations there. There's the word evaporation and there's the word vaporization. So evaporation can occur at temperatures below the boiling point. Water evaporates when it's just sitting out on the counter. Eventually, it takes a little bit of time, but it will eventually evaporate. But when we turn that, when we boil it at 100 degrees Celsius or 212 degrees Fahrenheit, that's what we call vaporization. And then sublimation is one that we're not as familiar with. We all know melting, and we all know evaporation. Sublimation is when you have a solid changing directly into a gas, skipping the liquid phase. So have you ever gotten dry ice, which is solid carbon dioxide, around Halloween? Sometimes people do that and put it in their punch bowls, or just to give you that fog effect. That solid carbon dioxide going directly from a solid to a gas and creating that fog effect is sublimation. You skip that liquid phase. The temperature difference is so great from the temperature of the solid carbon dioxide to room temperature that it just doesn't even melt into a liquid. It just immediately turns into a gas. We call that sublimation. Another form of sublimation that you'll see in the wintertime is sometimes you'll see a big bank of snow after it's snowed a lot and they've plowed the roads, and you'll see a big bank of snow on the side of the road. Well, even at temperatures below freezing, that stuff will eventually start to go away, because just like evaporation can occur below the boiling point, sublimation can occur below the point at which it would normally turn into a gas. So then we have exothermic processes, or those that involve the loss of heat energy. These are as follows. So freezing. So we don't tend to think of freezing as exothermic. We tend to think, if you watch my last video, exothermic, well, that's giving off heat, so that feels hot to the touch. Well, when we think about freezing, we don't think about something feeling hot to the touch. Well, obviously it doesn't. But what's going on there is the liquid is giving off heat, energy, and turning into a solid. Those particles in a liquid are moving around one another, and they have enough energy to kind of flow over each other, and we start to take some of that energy away, and all of a sudden they kind of are locked in place, and then they're just kind of vibrating right next to one another. Freezing point, as we all know, is the temperature at which a liquid turns into a solid. Condensation is when you have a gas turning directly into a liquid. So condensation occurs on a hot summer day. You go outside with a glass of iced tea, and all of a sudden you notice that the outside of your glass is wet. Where does that wetness come from? Well, it comes from water vapor or water gas in the air. When it hits the sides of that cold glass, it cools down very quickly and turns into a liquid. Again, what's the difference? Those particles are slowing down, they're coming together, and then they're kind of flowing around one another, turning it into liquid water on the side of your glass when it was water vapor just in the air. So the reason that happens so much in summer is because you have a lot of humidity in the summer, a lot of water vapor in the air, and that's the difference. Condensation point is what we call the temperature at which a gas turns into a liquid. And then finally, deposition. Deposition is something that we see a lot in the wintertime, but we don't ever think about it as deposition. Deposition is defined as when a gas turns directly into a solid, skipping the liquid phase. So again, in this wintertime, where the temperature outside can be very cold, you have water vapor in the air. And when it touches a very cold surface like the glass window of your car, instead of turning into condensation like it would on a hot summer day, it turns directly into frost. And that's a solid, that's ice that's forming on your windshield. And it's not from sleet or anything like that that's falling, it's just water vapor in the air that when it comes into contact with your cold windshield, turns directly into ice. So that's a gas, water vapor in the air, turning directly into a solid, the frost that you have to scrape off of your windows on a cold morning. So here's a graph just kind of showing all of that in terms of the endothermic and exothermic. So here we have sublimation going from a solid to a gas. We have melting, solid to liquid, and we have vaporization, liquid to a gas. And then going the other way, the delta H is negative, heat is being lost, gas to a solid, that's our deposition, gas to a liquid, condensation, and then liquid to solid is freezing. So we can take all of that and we can show it on a heating or cooling curve. Basically, a heating and cooling curve are the same thing. It's just that one is showing heat added, one is showing heat being taken away. And the difference in the graph is going to be, it's just going to be completely flipped or opposite. So heating and cooling curves are visual representations of phase changes. A heating curve shows the temperature increase as heat is added to a substance. So right here is our heating curve, okay? We're adding heat. Let's say we start over here with an ice cube. We start to add heat and we get up here and it starts to melt, right? It's 0 degrees Celsius or 32 degrees Fahrenheit is that freezing point, but it's also the melting point of ice, all right? So then we continue to add energy to, now let's say it's all water. We continue to add energy along this line and it all becomes a liquid until the point it starts to boil at 100 degrees Celsius or 212 degrees Fahrenheit. I keep using water as an example, but that's only because it's something that we're very familiar with. This is true for all pure substances. They all have their own heating and cooling curve, and they're all going to be dependent upon the substance as to where they melt, where they boil, and so forth. So then the opposite of that is our cooling curve. So a cooling curve is going to start out on the high end and go low, because the cooling curve shows temperature decrease as heat is removed from a substance. So now what we've got here is, again, keeping in mind with our theme of water, we have water vapor where we remove some of the energy and it turns into liquid water. We keep removing that energy and now it begins to freeze and it becomes solid ice. So heating curve is going to increase or go up from left to right. A cooling curve is going to go down from left to right. And so if there was one thing where you had to label a heating and cooling curve on your notes, well, right down here, this point, this diagonal line from here to here, that's when it's a solid. This diagonal line from this point to this point, that's when everything's a liquid. This diagonal point from here to here, that's when it's a gas. Well, guess what? You don't have a phase change and a temperature change at the same time. That cannot happen. Whenever something is heating up, that energy is being used to break bonds in between, in this case, the solid. So when I'm going from here to here, the energy is being used to break the bonds. Once I get to 0 degrees Celsius for water, that ice that I began melting continues to melt. Here's the phase change. These straight lines are where the phase change occurs. The diagonal lines are where the temperature changes occur. Heating curves begin with a solid and progress to a gas, all the way up to here. Cooling curves begin with a gas and progress to a solid. Diagonal lines indicate that a state of matter is changing temperature. Horizontal lines indicate a phase change. Again, notice you can't have a temperature change and a phase change at the same time. As long as that temperature is increasing, our solid ice is beginning to move faster until this point right here, and it starts to turn into a liquid. Then at this point right here, it's all liquid. And now if we keep adding energy, that liquid's gonna begin to get hotter and hotter and hotter until we reach 100 degrees Celsius and it begins to boil. So this is the phase change from going from a liquid to a gas. And then up here at this diagonal line, it's all a gas. So temperature remains stable or flat during a phase change to allow attractive forces to break apart or form between particles of a substance. Evaporation and condensation require a greater amount of heat change than melting and freezing because of the amount of attractive forces between the particles changes the most. So evaporation and condensation require more energy than do melting and freezing. And that is represented typically, what we'll have our shorter line here and a longer line here to represent that greater change in energy. And then again, refer back to slide 7 and refer back to what I was talking about there for labeling all of these solid, liquid, gas, freezing, melting, evaporation, and condensation. And basically, they're just going to be the opposite of one another. So if we label this graph here, it's solid, liquid, gas on those diagonal lines. And then freezing and melting occur along this line right here. So this would be melting on this graph. Here would be freezing. It's still, for both graphs, it's the same in terms of gas hot on the top one, liquid in the middle, and solid on the bottom. Then on this graph, for the heating graph, this line would be vaporization or boiling. This line would be condensation, and this line would be freezing. I hope that helps you understand phase changes and heating and cooling curves a little bit, and I hope you have a great day.